In previous chapters, we've talked about quite a lot of stuff. We've talked about option, result, we've talked about functions. And in this chapter, it's about time that we start talking about lifetimes. We've come across lifetimes a few times actually throughout the course up to this point, but I've jumped over them simply because I didn't really think that it was important at that point in time to explain how lifetimes work. But the more and more advanced we get at Rust, the more important it becomes to actually talk about lifetimes. And it is one of the most fundamental parts of learning Rust. It is, I would say, it is one of the most important parts of learning Rust. So it is essential that you don't jump over it just because it gets complicated or that maybe you don't think it is important, because I can guarantee you can't become a good Rust developer without actually understanding some of these rules. Actually, there are only 3 important rules to learn about when it comes to lifetimes, and I think you need to learn all 3 of them. So we can't really jump over any of them. So let's talk about lifetimes in this video. In order to explain lifetimes, we have to have a look at a few examples. So here's a function that we're going to write in here. It's called getFullName. And as you can see, it returns a string slice. So let's have a look at what this function does and how it actually works. So fn getFullName in here, getFullName, okay. And we're going to say that this is returning a string slice in here. And let's just say John Doe at the moment. Okay. So you can see as soon as you write this function, you will get this error saying missing lifetime specifier. This function's return type contains a borrowed value, but there is no value for it to be borrowed from. Okay, this is interesting. So if we change this function to return a string, and in here we set toString, you would see that, well, yeah, it's working kind of as expected. It's returning a string. So it is not a reference. It is an actual instance of an object. So how is this actually working that a string can be returned, but a string slice can't be returned? And this basically, we need to have a look at what a string slice really is. A string slice, as its ampersand before it basically indicates, is a borrowed value. It means that the string itself is being created somewhere, and then we're just borrowing a reference to that value. So if you think of in terms of memory management, inside the main function, if you call this getFullName function, as you can see in here, so let's say the application comes in here and then calls this function to grab a string. So calls this function, it tries to grab a reference to some sort of a string that probably sits in the heap. However, since this function itself is creating that string and just returning a reference to it, by the end of calling this function, that string space in the heap will be deallocated and will be not, it won't be available to the main function. So calling this function and returning a string reference, it basically is kind of saying that, hey, give me a borrowed value, give me some money, and then by the time that function is done, the money is gone. So you don't have a reference to that money. It was kind of a bad example, but I think you kind of understand the point. This is a borrowed value. It is not an actual. It is not an actual contained value in the heap, and Rust doesn't understand then how long it lives on for. So we need to help Rust in a lot of cases to understand where references are stored, how long they're stored for, and what their lifetime is. And this is the whole point of lifetimes in Rust. And we're going to look at some examples in this chapter on how we can fix these things. Okay. So what we can do in here is to solve this problem is to tell Rust that, hey, this string that we're creating needs to live on as a static string inside our application, meaning that it is basically a string that we've allocated. It needs to live in the heap or maybe even in the data stack of our application, depending on how Rust wants to compile the application. And it is available for the entirety of the application's lifetime. And I completely understand that all these ampersands and stuff that we write in Rust kind of make the code look complicated, but you just need to get used to them. I mean, there's no way around it. So lifetime operators in Rust add a little bit of complexity to the syntax, and they're written with just a single quotation mark before the data type, and then you would write in this case a static lifetime specifier. So what this is doing in here is saying that this string needs to live on for the entirety of the application's lifetime. So, and its lifetime is static basically. So now you see Rust is happy saying that, all right, then I understand that I need to store this in a place in the heap that lives on for as long as the application is running, meaning that the main function is, of course, going to have access to that string. Okay. Now, when you're writing functions, you can have also generic lifetime operators. As you can see, we have for instance, a function called getRandomName. So it takes two names and just returns one of them randomly. So let's just start writing that function without specifying lifetime specifiers. So get random name. And then we have one parameter in here, which is a string slice, str, and then another parameter, which is a string slice as well. And the function returns a string slice. Then in here, we just at the moment say a. Okay, so this is just a simple function implementation. You can see in here that we're getting the same error, missing lifetime specifier. Now in here, what you could do is to tell Rust that, hey, let's say the main function is calling. Let's actually call that function. So you can see the main function is creating the reference to those. It's creating those strings for us. So the main function actually owns the strings A and B. So what we just need to tell Rust is that for as long as A and B are living, I'm gonna basically I need the return value to also be living as long as that in the memory. So how do we do that? As you can see, we can go ahead and tell our function that we have two lifetime specifiers, A and B, and then we're going to say A has the A lifetime specifier and B has the B lifetime specifier in here. Okay, and the return value needs to live as long as A lives on. So you can see what we're telling Rust in here, that, hey, we get two strings. One of them lives as long as A lives. A as in like the A lifetime specifier, not the A variable. A just happens to be the same name as this one. It is quite complicated, but maybe we could just call these E and T or something like that. So we say E and T, for instance. Or I wonder if you can call it L1 and L2, as in lifetime 1 and lifetime 2. So let's say lifetime 1 and then lifetime 2, and we say the result lives on as long as lifetime 1 lives on. So now you can see the application works fine as well. So what we're telling Rust in here is that we're getting two variables. One of them lives as long as L1, the other one lives as long as L2, but the return value that we're giving back needs to live as long as L1. So in here, if we then change this to B, you can see that it says lifetime mismatch. So it says, hey, wait a minute, you said that you're returning a string slice that needs to live as long as lifetime 1 lives on, but you're returning a B value in here, which turns out to be living as long as lifetime 2 lives on. So the lifetimes don't match in here, okay? So what you could do in here is to actually say, okay, I just have one lifetime in here. Both are the same lifetime, or let's just call it L, okay? And then we go in here and say, okay, both L's in here, and the return value is also L, all right? So, and then we get this warning to snake case. Okay, so it wants us to use a snake case. That's fine as well. Let's make it a lowercase in here, and you can see then the function is compiling. So you basically need to think about when you're thinking of like returning references and you're returning objects that you don't own, you need to think in terms of their lifetime, how long they're going to be living, especially when you're working with string slices, for instance. Okay. So let's now talk about lifetime operators in structs. We did come across this problem, but I jumped over it quite quickly when we were talking about structs because that was not the time and point to talk about lifetimes. All right, but let's go a little bit deeper into that. Let's create a little struct in here called person. Okay, as you can see at the bottom screen. So let's say struct person, and then this person is going to have a name, which is going to be a string slice. All right, and you'll see directly that we're getting an error in here saying that, hey, okay, this is a reference to some sort of a string, but you're not telling me how long this guy is going to live on for. So am I supposed to carry this string for as long as the instances a person live, or how long should I keep this guy alive for? So what we could do in here is actually say that, okay, person actually has a lifetime specifier, and the name of the person also has to be available for as long as the person instance itself lives. So this then gets rid of our problem for us, meaning that, yeah, basically, if you create an instance of person, the string that you specify as the name of that person has to live on for as long as the instance lives. And that kind of makes sense as well. But you'll also sometimes see people writing code like this, or oops, static, meaning that, hey, this string that we're specifying as the name of the person is kind of going to live on for as long as the application lives on. Okay, so that's also valid code, but I suggest that you have a think about how long your references are going to be valid for, and specify lifetime specifiers according to that. Okay, so we've already had a look at this. So I just brought up the label simply because I had it in my deck in here, but you can specify your lifetime operators or specifiers as we've seen in here. Okay, now there is a very strange example that I want to bring up in here, which is going to be yeah, it's going to be a little surprising. So let's just write the function get first name, we call it, okay, and then we specify the full name in here, and we say this is a string slice, and in here we just say we also return a string slice, and for that we just return the full name. Okay, so nothing special in here. If you look at this code, you'd be like, oh, but wait a minute, this guy's returning string slice, but it's compiling fine. I thought that we said if you're returning a reference, you have to specify how long it lives on for. And this is the weird part about, actually, I don't want to call it weird. This is one of the quirks of 3 of the lifetime rules in Rust, which we are going to have a look at right after this. But there is a specific rule that the Rust compiler engineers have applied here to this particular function, which is hidden from our eyes. But what is happening here is that Rust is automatically assigning lifetime operators to both this parameter and the result value. What is happening here is Rust is basically writing this code for us. It's saying that this is A, and this is A. So it's saying that whatever lifetime the parameter, which is a reference, has, so if you have a reference parameter, the result also is going to be having this exact same lifetime. So this is one of the rules, and it's hidden. You don't see it being applied, but we're going to have a look at these rules soon. So I just mentioned that there are 3 rules for lifetimes in Rust, and let's just dig into them and see how they look like. So the first rule is that if you have parameters to your function and their references, the compiler automatically assigns a lifetime operator to each one of them. So if you had 2 lifetime operators, 2 reference parameters in here, then the compiler will assign 1, 2, and 3 lifetime operators. So the first one gets the first operator, second one second, and third one third. So you basically don't see it happening, but it happens automatically. So just keep that in mind. 3 parameters, 3 lifetime operators without you actually knowing. 1 parameter, 1 lifetime operator without you seeing it. Okay. Now the second lifetime rule is that if you have a single input reference, a single parameter that is a reference, the lifetime that is automatically assigned to that single parameter is also going to be in a hidden way automatically assigned to your output if your output is a reference. So that is the second rule, as you can see, being applied here. Basically, this is a combination of the first rule and the second rule being applied here. So Rust had a look at the first rule and was like, oh, I found a reference parameter, automatically assign A to it, okay? And then it puts the A in here as well, okay? But this isn't complete yet. Then it goes to the second rule. It'd be like, oh, the result is a reference and the parameter is a reference. They have to get the same lifetime operator or specifier. So you can see basically it completes the picture with just rule number 1 and rule number 2, okay? Now, rule number 3 is if you have a reference to self or a reference to mutable self, which you saw in implementation of structures, for instance, when we're talking about methods or class methods or struct methods, is that if you have those as parameters, then the lifetime of self is assigned to the output. So it's quite easy. So if you have a reference being returned from one of the functions, and the function has a reference to self or a mutable self, then the lifetime of self is going to automatically be assigned to the lifetime of the output or the result of your function. So these are the three rules, and it is quite important that you actually think about them and let that coin basically drop in your brain before continuing with the rest of this video. Now, let's go ahead and define a person struct in here with a first name and last name and just one lifetime specifier. So let's say struct person, and we say a, and then we say first name is a string slice, and then we say it lives as long as the person instance itself lives on, and then we say last name as well, as you can see at the bottom of the screen. So what this is telling us is that we have a person instance, and these two string slices should live on for as long as that instance of person basically lives on. Okay. Now, if you're working with structures that already have lifetime specifiers and you want to create implementations for them, then in your implementations, you also have to specify your lifetime specifiers, as you can see at the bottom of the screen. So IMPL, and we say the lifetime specifier of A, we're working with a person that lives as long as A. So this is how you would basically create an implementation block for your person. So you could try to remove these as well, as you can see in here, but then you get this error from Rust. So that's how you would basically create your implementation for a structure that has a lifetime specifier. Okay, but that's not all I wanted to talk about with this implementation block. We're actually going to go ahead and create a function on this implementation block. So we want to get the first character of the first name from this person instance. So we want to create basically a function in this block which references self. All right, so let's go ahead and say fn first char of first name, and we have a reference to self, and we're returning also a string slice in here. So str, okay? That's really good. And then after doing that, we're going to go ahead and say that we're going to take first name. Actually, this is a pretty good suggestion. So we could use that. It is exactly what I want to write. So this is really good. So what is happening in here is that we're referring to the first name string slice, and then we're saying that we're going to go from 0 to 1. So we're getting the first character out of the string. So what's happening here? You can see that we have a string slice being returned, but nowhere in here are we specifying the lifetime for the string slice. So what is happening is that we're hitting lifetime rule number 3, which is as long as you have a reference to self and a reference being returned from a function inside this implementation block, then the lifetime of self will automatically be applied to the lifetime of your reference output. And this matches really fine because we're basically saying that both these string slices live on for as long as the person instance lives on. And that is fitting really well into the lifetime rule number 3, basically saying self lives on, or sorry, the string slice lives on as long as self lives on for as well. Okay. Now, let's go ahead and say we want to return a full name in here, okay? So we create a function that is called full name, and we want to return a string basically out of those two string slices. So since we're creating a completely new string, then we're actually going to return a string instance and not a string slice, okay? So let's say get full name, and then let's see if we can get some help from it here. And this is actually pretty good. So it returns a string. So what is happening here is that we're basically, you can see in here, this string is not a reference, so we don't have a problem actually returning it. So this string is gonna basically be living on for as long as the caller needs it for. So no lifetime operators need to be specified in here because this is not a reference, okay? Now, you also have ability to specify lifetime specifiers for specify lifetime specifiers. It's quite a lot of specify stuff I'm throwing out there. But you can mention, or actually specify is quite a good word. You can specify lifetime specifiers even for enums. So for instance, if you have an animal in here which has a name, so let's say enum animal, okay? And then if you go in here and say that we have a dog with a name, which is a string slice in here, okay, you can see by default you get an error because Rust doesn't know how long this string has to live on for. But you can turn this enum to having lifetime specifiers, and then you can actually say, as long as that enum instance, which in this case is dog, as long as that enum instance lives on for, the string slice also has to live on as long as that, okay? So lifetimes are fundamental to knowing how Rust manages memory. But for me, what made it a lot easier is you need to think about how Rust is trying to not be like C. C was kind of like a wild, wild west, and is like you allocate memory and you're responsible for deallocating it. However, Rust is trying to not do that, saying that if you allocate memory, I'm going to deallocate it for you automatically. So first is going to try to deallocate something for you. And also, secondly, it wants to not double deallocate something. Okay. So that's why Rust is a lot safer than C. So if you think about Rust trying to deallocate things for you, it kind of needs to know how long things need to live on for. And that's what lifetime specifiers are for. You need to help Rust sometimes to say, hey, here's a string slice reference, and it's going to need to live as long as A or B or C, blah, blah. Okay. So I understand that we haven't really, we've just touched the surface of lifetimes in Rust, but we're going to see more examples of this, of lifetime specifiers throughout this course. So I would really suggest that at this point, you maybe grab a cup of tea or something and sit down and play a little bit yourself as well with lifetime specifiers. And remember, they're useful when you're working with references. So create a struct or something, add some lifetime specifiers to it, and have that struct have like a string slice as one of its properties, and go in some functions and return an instance of a reference to an instance of that struct and see what happens. So remember, references and lifetime specifiers go hand in hand. So hope you enjoyed this part of the video, and I'll see you in the next section.